Hi, everyone. Welcome to Machine Learning and Friends Lunch. Today, we are super happy to have Professor Wei-Chiu Ma as our speaker. Wei-Chiu Ma is a professor at Cornell University. Prior to joining Cornell, he was a young investigator and postdoc at AI2 and University of Washington. He received his PhD from MIT, where he worked with Antonio Torralba and Raquel Orderson. Previously, he was a senior research scientist at Uber Advanced Technology Group R&D and will be working on self-driving vehicles. His research lies at the intersection of 3D and 4D vision and robotics, interested in building AI systems that can understand, reconstruct, and resimulate our dynamic world. We are very excited to have him here today. Please join me welcoming Professor Wei-Chiu Ma.
Let me see. Okay, great. Yeah, thanks for having me today, and thanks for the kind introduction. Hi everyone, I'm Wei-Chiu from Cornell, and yeah, as you see from the title, today I'm going to talk about some of our group's recent efforts on how do you construct digital twins from the real world, and how can we use them for in different use cases, from like training robots, from using them for cross-embodiment learning, and also if we have time, I would like to show you some interesting how we can use them to create some arts. Like I think it's really cool. Okay, so I'm going to start with a bit generic intro. So wait, please bear with me if you have seen similar things. So nowadays we see like there's so many progress on these like generative AI, right? Like vision and NLP. I think we see like tons of progress. I personally use Claude Code every day, and I use GPT to help me like refine my emails or writing and all these things. And the secret behind these things, I think we can all agree that it's just tons of data, especially high quality data. So these things have been the fuel behind all these progress. But then the question is, how come we don't see similar things in robotics? When we think about robot learning, all these things, although we see lots of good progress here, like VLA and all these things, but somehow comparing to the progress in vision and NLP, things are still lagging behind a bit. And the question is like why this is happening. And of course, one of the key reasons over here, or at least I would argue, and I think many of us will agree, is that we just lack a high quality or large amount of robot data that can help us learn these kind of robust policy that can transfer to the real world or transfer to all sorts of like in the world situation. And one reason, of course, is, okay, this is very expensive to collect. And this is a slide I stole from Kevin Black, but for those who have seen this, I think it's really nice, so I still want to show this. It's just to give you a sense about what is the scale of existing robot data set. Of course, there's lots of companies that collect their own closed source data, but outside, really these two are the data set that people usually try to use, which is like Droid or like OpenX. So it seems a lot comparing to what we have before, because usually we just collect these things in the lab setting and then do our own stuff, right? And now we start to compile things together and have a much larger scale things. But if you compare really to what these large models have seen before, the scale is different. So even GPT-2 that happened like 5 years ago, okay, or 6 years ago, I forgot exact years. If you assume that every human can read 240 words per minute, then GPT-2 has already seen data equivalent to almost 500K hours. So if you think very closely, it's just like 1% of the data of those GPT-2. And if you really think about the largest model these days, even not the largest, even the Llama 3, just Llama 3 itself, it's almost like 800 million. So the robot data that we have right now is only like 0.001% of what we have. And if starting from nowadays, all of us stop sleeping, stop working, and collecting data full time, it may take us like 8 or 9 years to achieve that level. So the scale of the robot is like, the robot data is like really one of the key things that kind of hindered us from moving towards there. And of course, let's say today, if we will just do this and start collecting data, it's still very expensive to do so. So for those who are not familiar with these things, I'll just give you a quick overview about, okay, how people collect robot data these days. So just don't you take a look. So this is one of my students. He's trying to practice how to do teleoperation to collect data over here. And you can see that his facial expression is very serious. Like he's very focused, and he moves his whole body all together with a robot, like moving forward, all these things, although he doesn't need to do that. But he just do all these things in order to get these kind of data. So it's actually a very expensive operation. Oh, by the way, he doesn't know I put him on the slides. I just told him I want to record this thing. But anyways, yeah. So the nice thing about this is we got realistic data, right? But of course, you can see that it's super expensive to do these things. So of course, ideally, if you want, is we want the robot to explore the world, and then maybe they can use this exploration and then just get some high quality data themselves, right? But of course, if you look at the thing on the right, actually, it's still like this way. They actually put a phone and do these things. It's not like automatic. It's kind of a human. So thinking about this, we can see that, okay, real robot data are great, but we just cannot get them. So what are the alternatives? So of course, now people are thinking about simulation. And I guess a lot of people, folks here, like Tron, also doing a lot of these works over here. And one nice thing about simulation, we know that it's controllable. You can have assets. You can put it in whatever layout you want. You can have infinite of them. But if you look closely at them, of course, you'll notice that they're not realistic enough, right? And one thing that people often ignore is actually it's super expensive to create these digital twins, or especially these simulators. So just to play a game, to give you a sense about how expensive these things are. So here's the thing, there's a game of a screenshot, right? And then I would like to ask you, how much do you think it will cost in order for artists to build these assets over here? So for instance, can people guess like how much does this truck over here cost? Be bold. It's expensive. Oh, 100, okay. Okay, 10,000. Okay, so and this one's actually cheaper. I think it's only 5,000. Okay, what about the trash? 1,000. Okay, the trash worth 1,000 is very ironic, and it actually costs 3,500. And if you look about the big trash, it says big in front, so you can imagine it's costing more. So the big trash actually costs more than like 10K. It's like 14,000. So basically, what this is telling us is, even when we want to do simulation, it costs us so many money in order to really like have artists curate these assets, make sure they are articulable, and try to give them the right physical properties and all these things. So this makes us wonder, is there a way that we can kind of automate this pipeline? Can we try to get all these things in an automatic fashion, and at the same time try to make them as realistic as possible? Okay? So this is what we are aiming for today. And of course, there's some concept called digital twin, right? Basically, can we build a digital twin that's exactly the same as our real world? And for those who didn't hear about this term, I'll quickly introduce it. For those who already know, give me 2 more minutes. So digital twins is a concept have been around for a while, but I think the first time it appears kind of in like 1960s. Okay, so at that time, NASA they built this really nice digital twin of the spacecraft, and then they used this to help train astronauts how to like land in the moon. And at that time, there's an oxygen explosion. So actually, this digital twin really helps them to simulate all sorts of scenarios and help them land safely. And around the same time, I think a graphics researcher, Ivan Sutherland, he also proposed very similar concept. And I really like the thing that he described this thing. So he's basically suggesting that the digital twin should look real, act real, sound real, and feels real. Okay, and then we are just using a kind of these ultimate display in order to connect to this virtual world. And both of these things, they propose the concept in a different context, but all of them are suggesting the exact same thing, which is the digital twin and the world should have very strong binding, which means if something happened to the real world, the digital twin should respond in a correct way. Okay, and then a digital twin should not just look nice, it should also have some physical properties so that it looks real, or everything is physically plausible. Okay, so if you put it into layman's term, these are key things that I will argue are key things for digital twins. Is first, it should have high fidelity. Not just as a vision person, I want it to look nice. I want the geometry to be good in order we can compute collision and all these things. And the second thing is, we want it to be interactable. So we want to be able to push this bottle over here and move. We don't want things to be static. And we want it to respond in a physical plausible way. And the third thing is, we want it to be real time. Okay, so these are kind of some key properties we're looking into. And today I would like to share with you some of our recent works on how can we build digital twins that have these kind of properties from the real world in automatic fashion. And then hopefully we'll also talk about, that's the first part, and then we'll talk about how we can use them in different ways. For instance, from the basic way of training reinforcement learning agent inside to more creative use of using them to align humans and robots and different things. Okay, so one easy way, one straightforward thing to go from real world to digital twin, I guess, is just 3D reconstruction, right? Nowadays, we see these nice things like you have these set of images and videos. You can just estimate the underlying 3D like very easily. Of course, if you want, you can look at it from different perspectives. And if you parameterize closely, you can recover these like super nice geometry as well, where you can like look at these things from different angle and compute collision and all these things. So this is super nice. And then because of these things, people are starting to say, oh, this is a digital twin. We can use them to do all sorts of things. But the key question is, these digital twins, what stops us from using them is because they are not interactable nor actionable. So what does this mean? So imagine today you want to like develop a robot in your kitchen. Okay, so you are going to use 3D reconstruction and then build this scene, and you start putting your robot into the simulator. You want the robot to like grab something from the drawer for you. You want it to give the cup to you over here. So you'll start applying actions like sliding the drawer out or moving the cup. So ideally, you want the cup to move this way. But when you really apply these actions, instead of following what you imagined, what really happens is the whole scene will move together. And why? It's very obvious, right? If you look closely, the drawer is actually attached to the bottom thing, and the cup over here is actually attached to the countertop. So what is really missing here, besides these like geometry or visual fidelity, what is really missing here is a nice physical understanding of our world. Like, what is the compositional structure? What is their articulation? Is this a revolute joint? Is it a prismatic joint? What is their affordance? What happens if I open a drawer? What's inside? Can we put stuff into it? Those are the things that we really need to answer in order to have this digital twin to be really powerful, and we can use them for other robotic purposes. So today, okay, so the first work I'm going to talk about is one work that we just presented at CVPR that's led by Wei-Chiu. So we are going to see how we can do this thing. So here's our setup. So we have this real world video, okay? So this is a person capturing the video. You can see that everything's static, just a pure passive observations. Our goal is to go from here to a thing to the right. Of course, not just that, we want to infer all these articulations and what's inside. How many layers are there inside the cabinet? What are the textures? What are the geometry? We want to estimate all these things. That is our goal. Of course, the first question I think maybe is, how do we do these things? First of all, how can we get a nice geometry and nice visual fidelity? Of course, now we see a lot of things. For instance, people heard about Gaussian splatting. They look great in terms of RGB, but the geometry just sucks. And then another thing is we know, okay, there's neural SDF that gives you really high quality geometry. But when you render RGB, sometimes the results are just a bit subpar. So looking at these, it makes us wonder, do we need to compromise somehow? So do I need to have a digital twin that only works good on one thing and worse on the other? So then we start to think, is there a way that we can somehow combine the advantage of all of these things? So our idea is, can we use a thing called dual representation? So instead of only using one single representation, can we use both and enforce a very tight coupling among them? So for instance, here's our idea. We first use neural SDF to create this really high quality geometry of the scene. So you can have a better estimate about those occupancy grid, so you can compute collision and all these things. And then in order to enable all those visual motor policy, we start to place all these Gaussian splattings, Gaussians, on the zero level set of these neural SDF. We ensure that these Gaussians lie very close to the surface so that there's no floating Gaussians. So in this case, we can still preserve this high quality geometry, but at the same time, we can leverage the Gaussians' expressiveness to capture the RGB. So by doing this very simple thing, you can see that at the end, we can kind of preserve both nice geometry and very good RGB. Okay, once we have this representation, the next thing is, okay, we have this nice 3D thing. We still have the question about, okay, what if I interact with the scene and the whole scene will move together, right? So our key idea is first, can we imitate what humans do? Can we first recognize what objects are of our interest that we want to interact with? For instance, we can see that, oh, the kettle over here, it's a rigid body. is movable. And we look at the cabinet over here and say, oh, this cabinet, it can be opened. So we first try to identify all these objects that we want to interact with, and then we try to locate them in 3D. So what we'll do is we'll use 2D foundation models in order to estimate them across frames and then fuse them back into 3D. So this allows us to get rid of all those redundancy. And the nice thing is all these things are grounded in 3D. So I'm going to show you very quickly that once you go move these things into 3D, we can estimate these physical properties very easily. Okay? So now we have these things in 3D. The next question is, how do we know what physical properties they have? And of course, I think as humans, we can easily tell that these materials are like wood, right? And we can imagine, or we can look at the book to see what is the density of a wood. And we know their volume, so we can compute their mass and all these things. So basically what we'll do is we'll take these things and we'll ask these VLMs about these questions. Okay, what is the density, or what is their usual mass? And also, for instance, what do you think their articulations are? So in this case, we can know that, oh, actually, these things, they're actually a revolute joint, because when people open the cabinet, they open it, like they will rotate across the axis. And the drawer over here is actually a prismatic thing. So when you apply a force, it will slide it out. And the nice thing about these things is, since we ground everything in 3D, so the moment we know it is a prismatic joint, we can directly infer the direction directly from a surface normal. And the moment we know it's a revolute joint, we know it's on either side, so we can directly get a very precise location about these things. And once we have these things, the next step is we can start interacting with them. But then one obvious question will appear is that if I start opening this cabinet, what will happen inside? We never see anything inside. So if you just open, it'll just be black, like be empty. So the next step finally we have is we use something that nowadays we have everything we want, like we have tons of data, we have lots of nice generative AI models. So what we'll do is we will start with a simple template. We know this is a cabinet. We have so many nice template assets. And what we'll do is we'll take all of these template assets and then use differential rendering to fit them into the 3D scene. And then we'll make sure that they don't collide in 3D. When the door opens, they don't collide with each other. And we'll use standard differential rendering to put them in place. And we make sure when they render back to 2D, it looks right. And once we have this geometry, then we use generative models to implement their texture. So with all these things, this is kind of a pipeline over what we have. I'll just directly show you some really cool results that I personally like. Oh, before I show them, just to show you some of the comparisons, like this is the input kitchen that we have, and the bottom right is ours. And you can see that our reconstruction is exactly as what the input image looked like. Whereas the previous approach, they usually sacrifice in terms of like fidelity or texture and all these things. And just to give you an example, I think it looks a little bit worse on Zoom, but I can show you more videos later. So you can see that there's different kitchens, and we can just, from a passive video, we can reconstruct all these interactable scenes from here. And of course, the next question will be, okay, these look nice, but you're just a vision person. Did it really follow those physics, or did they really, the motion looks realistic in 3D or not? So the first thing we can look at is, okay, first of all, how accurate is these like reconstructed axes and these things? And you can see that ours are like very aligned because we do everything in 3D. And the second thing is, okay, even if you do these things, do they really, the motion, how are they doing comparing to these video models? So you can see this thing. If we compare this with a video model, which take in a mask and an action, this is what they generate. It looks pretty nice, to be fair, but then it's just like they cannot understand all these like, composition of the world. Whereas in our case, since we explicitly model all these things, we can just plug into a simulator and then animate and then like, start animating all these things. And another thing is, these looks nice, but dude, are they really, really physically possible? So this is my favorite part of the experiment. So we have this refrigerator. So my student, Hongchi, he take a fish wire and go through all the refrigerator, and he's outside the video, okay? So then he used a fish wire to open the refrigerator so that you can have a ground truth about how this door opened. And then once we have this thing, we annotate a few points on the plane and use homography to interpolate across the full plane. So we get a ground truth trajectory. So those ground truth trajectories are in red. And the blue ones are just our simulation, and we align them back to the scene. And you can see that they basically just align with each other. So what this is telling us is how accurate. So of course we have accurate numbers. I didn't show here, but if you look in the paper, we have a very comprehensive study. So basically it's suggesting us when we try to estimate these different revolute joints, prismatic joints, the 3D motion that we recover is actually aligning with what really works in the real world. Okay, and of course, I think this thing can apply more than kitchen. You can do this to office, or you can do something to the toilet. And rest assured, I think this is a clean version of his toilet. So I asked him to clean it first and then record it. Yep. Okay, cool. So, and of course, beyond this thing, we can also go to outdoor scene. So this is another of our previous work, how we apply similar concept to outdoor. And you can see that we can convert a self-driving scene into a thing that where you can just interact with it. So you can drive a car inside, you can bump into them. And then since we estimate these physical properties, we can just apply rigid dynamics to simulate all these things. And of course, all of these things that we do is code is released, and you can combine with Unreal Engine and do all sorts of gaming things if you want. So in this case, you can just place a kettle in different places, and you can just directly do all sorts of shooting things. Okay. So now we have seen, okay, how we kind of go from a passive static video into this digital twin. The next thing is, how can we use these things to unlock the potential of like some robotics or other autonomous agents? So one thing I would like to first talk about, of course, one thing very obvious is, okay, this case. So bear with me with this quality. I think this is not the latest version, but the latest version, the quality is much better. But you can see this is just an example of how we do things. So we can just spawn tons of robot arms in the simulator and then have them to do different things. In this case, open a drawer, pick up one thing and put it in. So you can just imagine once we scan the kitchen, we can just spawn tons of these robot arms in the simulation and start doing our reinforcement learning. And once you do these things, it can be zero-shot transfer into real world. I think that is the exciting part. So oops, sorry. So you can see it will open and then, yeah, it's slow. It's not speed up, but yeah, it was success. Okay, cool. So now we can see that the first purpose is just using this to train reinforcement learning. But we all know that reinforcement learning is not efficient. It's simply inefficient. We need to spend tons of time. We need to do a lot of reward shaping manually. It's just hard. So we start thinking, is there a way that we can speed up this process? And our key intuition is, okay, how about we do this by watching humans? And especially humans have to interact with objects a lot of times. Is there a way that we can learn from humans? And of course, there's a lot of work that have been along this route. But what we are thinking is, can we combine human observations and use digital twins as anchor, as a bridge to tie these two things together? Okay, so that's another work that we just presented at Curl, done by Pratish and Kushal. So apparently this thing is very hard, just for those who are not familiar, because if you look at what humans do, human and robots has a lot of mismatch. There's dynamics mismatch. You can see if we, okay, maybe it's too fast. Let me just go through this again. If you see a human grabbing the shoe this way, it looks fine. But if you have the robot to do the same thing, it can really lift it, but because of the dynamics mismatch, it will be tilted, and then you cannot successfully complete a task. There's also kinematics mismatch, which means that if something like this frontal task works for this putting this cup on the tree rack, but robot arm cannot do it just because of the degree of freedom. It will just get stuck over here. So apparently it's just really hard. But then we start to think about, what does it mean to achieve a task? What does it mean to complete one thing? So if you think very closely, if I want to put this cup onto the rack, I can use a frontal grasp to put it there. I can also grasp it on the top and put it this way. So these two things, if you look very closely, their actions are very different. But actually, the objects follow very similar trajectories. So we start to think about, maybe instead of viewing things from an action-centric view, we should start to think about from an object-centric view. So maybe all we care is whether this object can induce this kind of trajectory. I don't care what action robot is applying. I just want to make sure that they apply certain action such that the objects move in a very similar way. That's all we care. So that's a key concept. So we move from this thing, we start to first, what we do is we use the first work that we did. We build the simulator from the real world. And then we have these human observations. Since we see human moving these things, we can directly replay the motion of objects in simulators. And then we start to do reinforcement learning inside, but instead we have a very strong reward to enforce that these agents, the actions that they induced will make the object follow very similar trajectory to the human trajectory. And then we train this RL in simulation, and then again we deploy into the real world. So basically, we use digital twin as an anchor to replay all these object trajectory and to try out which actions that will lead to these things. So if I want to summarize, that's the intuition. Here you can just see we have policy over here. We have a virtual environment. And then we just start playing different actions. And we just compute the reward as the difference between the motion caused by human and the motion caused by a robot in simulator. And then we use this and start learning. And we just keep using this. And of course, in order to speed up training, we first use privileged information about all these joint, for instance, object poses, object speed, and all these joint information. And then later on, in order to transfer it into real world, we start doing all sorts of distillation. We change the lighting. Like you can see, we change it to a very weird blue lighting. We change the viewpoint to make sure it's more robust to the real world jittering, all these things. And then we distill them into a more robust visual motor policy. And let me just start showing you some results. You can see that for simple task, human move this to this way, the robot can do it very easily. And you can see that the way the position they grasp are very different, because they don't care about whether they imitate the actual action, they just care about whether the object parts move in a similar way. But there's always a catch. So if we go to more precise tasks that we saw earlier, putting things onto the rack, you see that humans do it very well, but if you train it this way, sometimes there's a slight mismatch. For instance, if you look at the right, it's almost there, but it's just not there, like missed by 1 inch. So then we started thinking about, okay, what happened over here? And then we started doing all sorts of things to align the digital twin with the real world. We try to add more sophisticated shadow. We use PBR rendering. We try to look at the dynamics, all these things. But then ultimately we notice at the end of the day, no matter how, for instance, in terms of shadowing or these things, no matter how hard you try, if you train the policy, there's always kind of a mismatch, because the model will kind of like exploit these kind of small, kind of tiny adversarial things, and then leads to a different policy. So we are saying, okay, if we cannot handle this in training, can we do this at test time? So then what we do is, oh yeah, sorry, I just covered this. So you can see that this, no matter how hard we try, there's still kind of visual appearance across these things. So what we try to do is this thing, is we use this like test time alignment technique. So basically, whenever we have a robot execute a policy in the real world, we first, of course, we just unroll this in the real world, but at the same time, we try to have the digital twin do the exact same thing. So you can see that when I start to execute a policy, I have it to do the exact same thing in the digital twin. Okay? And then once I have these two, I have the observation from real world, I also have the simulator, then we will pass these two things into deep neural networks and then try to look at their visual embeddings. And then we try to enforce that these two things align with each other. So every time when you start to execute a policy, for the first 2 steps, we use this way to to fine-tune the model weights a little bit more, to align the visual features. And then once you align, then you start executing the rest of the thing. And with this thing, you can see that before it missed by 1 inch. And now, after this kind of online calibration or online test time alignment, inference time alignment, whatever you call, or domain adaptation, whatever, it can kind of mitigate the gap and then really aligns to this thing. Of course, if you want to say what is the caveat over here, is that you need to have this kind of test time alignment thing every time you execute a task. So it's kind of a bit of extra overhead when you're executing. But
yeah, it's cool. How is it generally right? I can't quite tell if you have a curious training, but how
I see. Oh yeah, okay. Maybe one thing I didn't mention extremely clear. Oh, and are there people online? Let me check. Okay, so there's a few. So the question was, how well does this policy generalize to, for instance, maybe different objects, different colors, or those things. So the setting we are tackling here is a real to sim to real setting, which means that we assume we just operate in this environment. So we kind of build the digital specifically for this environment. So today, if we train in this environment, we have a policy, you suddenly give me a completely different things, yeah, it will not work. But I think it will work in the sense that if it's in this environment, the lighting is different, the camera view is different, the object place is different, those things, it will work. Yep. Okay, and of course, this is just a minor advantage. It's like through this case, we can use human data to learn, and it's just much more efficient. Okay, but now we're still using reinforcement learning. So in some sense, we have a better human target as reward that can help you speed up, but still not fast enough. So we start to think, is there a way that we can do imitation learning where we have more direct supervision? Is there a way we can directly train our robot policy on human data? Of course, okay, so this leads to another work that recently we just submitted called cross-diffusion. So you might think, okay, Wei-Chiu, you're kind of saying something that contradicts yourself. Because let's say arranging a task, let's say we want to arrange a plate over here. This is how human will arrange it. Oh, sorry, a robot will arrange it. If we want to move the plate from here into over there, the robot will just push. But as humans, what they will do is human maybe will grasp and then lift it up and put it down. So like you mentioned before, things are very different. In this case, how can you just directly learn a policy on it? Of course, I guess now people have been very creative in ways. For instance, people will say that, oh, even though, for instance, robot only have 1 degree of freedom, you can see over here, we can try to make our hands look like robot gripper. And then we can also try to retarget these things into different number of key points, let's say over here. So in this case, maybe you can just do it. But the thing is, if you really think very closely, let's just remove all these images. If you just look at top and bottom, they just look very different. So even if you kind of abstract away all these kind of embodiment difference, or you try to have humans imitate all these things, at the end of the day, all the kind of statistics, they are just so different. So if you directly learn a diffusion policy on top of it, things will just not work. But then we start thinking about it. What is diffusion policy doing? You try to add noise and try to predict the noise, right? So let's take a look what happens if you add noise to these kind of action trajectories. Originally, it looks very different. And the moment you add more noise, they start to look a bit more similar. And the level of noise becomes larger and larger. These trajectories become more and more similar. So basically what this is telling us is the more noise you have, the difference between the action trajectory from different embodiment the gap between them start to become smaller and smaller and smaller. So in this case, we can use arbitrary data either from robot or from human. Doesn't matter. So this is our intuition. So this is how people train diffusion policies. They just use robot trajectories. They take these trajectories with different noise and predict the noise. What we do is, instead of this thing, we also include noise trajectories from humans, because you cannot tell whether this looks like robot or not. So they're similar, so we can just use them into training. Okay? And then if you look at the pipeline, it's kind of like this thing. So nowadays, let's say we have different data. We will first abstract them in the way that we are interested in, and then we will just add noise. And then we have we train a classifier to predict, can you tell this is from human or this is from robot? If they can tell this is from human, this means it's just way too different. We just throw it away. But if it cannot tell, if it's confused, we know that they are fairly close to robot. So then we include them into the data and start training. So you can see this as a very easy way that you can just mine through all sorts of human video and find those human videos that look similar to robot trajectory and then use them for training. And just for a comparison, again, this is just to give you a sense about the difference between the existing framework and our framework. Again, the bottom is the robot demonstration. The top is the human trajectory with different noise. If it's a standard diffusion policy, people only train on robots. So you need lots of robot data, and then, yeah, it doesn't scale that good. And when people do co-training before, they simply use all sorts of data together. And whereas in our case, so sorry, the color wasn't very clear over here, so there's something over here. It corresponds to this over here. And what we do is, instead of using every data, we only use robot data plus the top right, where those human data looks like robot data, okay? So with this very simple change, we can improve the performance by a lot. So you can see that on the rightmost green one is our bar, and the blue one over here is the standard one, which is the A over here before, and the middle one, pink, is the one of simple co-training. So you can see that with this very simple data filtering strategy, we can just improve the performance across a lot of different tasks. And of course, if you say why this may be one intuition, is you can see that if you do co-training, sometimes it will learn some very infeasible human actions, which is grabbing from the side. And then this part will just get stuck. But with our filtering, we'll just filter those things away, and then it can just still learn a more robot feasible solution. Okay. Okay. So now we're going step and step further. Now we go from reinforcement learning and say, okay, imitation learning. Another question is, let's say today we are in academic labs. Sometimes we don't have enough GPUs. What if today I don't have any GPU to train any policy? Is there a way we can use digital twins to directly unlock like robot learning directly? So that's what I'm going to talk about next, is how we can just combine digital twins with off-the-shelf vision language model without any tuning and just directly start executing. Okay? So this is work done by Chuanruo that we just presented RSS also in the summer. So again, here's our setup. Let's say today, why this is hard? Because today, if you tell the robot to throw, okay, today if I ask them to do, say, I want to pick up this angry bird and toss it to hit those toy pigs on the bottom left. It actually requires you to do two things. You need to do semantic reasoning. You need to first know that, oh, okay, this is the angry bird, and like this is the toy pig on the bottom left. And then once you know these things, another thing you need to know is you need to do physical reasoning. You need to know that, oh, which direction I should throw this, and at which speed. And then you find the one that you want, and then you throw, right? But the question is, how do we do all these things together? Because apparently there's just so many things to do. If you want VLM to do all these things, it seems very hard. And the nice thing about this thing that we are observing is existing VLMs, well, they are never trained to predict, say, oh, I need to move a robot for 10 centimeters or 20 centimeters. They're very good at semantic reasoning. And at the same time, digital twins are very good at doing all these physical simulation. So is there a way we can combine these two together and let digital twin do the physical reasoning part and let the VLM do the semantic part? So that's how we are going to do this, okay? Oh yeah, and previous work, sorry, just one slide. Previous work, what they do is they use different kind of visual prompts to do different things. But of course, one caveat is that if the VLM changed, then the whole work might just become deprecated or those things. So our key intuition, like we said before, is VLM is really good at these semantic reasoning. So let me explain what this means. So today, if I say I want to toast a bread, and I give you these two images, and ask you which one do you think is better? And oh, by the way, this is a robot gripper, and there should be a robot arm here, but we didn't render it. Otherwise, it'll be too cluttered. And every VLM will tell you actually the left one is better. And why? Because this is the bread over here, and the grippers at this angle is very close to the bread. So VLM don't know what to do, what exact action they should execute. If you give them different images and ask them which one do you like more, they can tell you very reliably. Okay? So this is exactly what we'll do. So first, when we have this scene, we'll first scan the scene over here, and then we'll use the first paper that we had to kind of reconstruct this digital twin. And then, of course, we'll both have appearance and also have the mesh about these things. And then next thing what we'll do is we'll put these things into the simulator, and then we'll simulate all sorts of outcomes of different actions. So you can see over here, we start to throw it at different angle, at different forces. And you can see that this one, it hits the vase, so it's definitely not good. So once we simulate all these results, we'll take the images and then feed it into VLM, ask them which one do you think are the best. And they'll look at the results, they'll see, okay, this one actually really hits the angry bird, so they'll pick this one. And then all you need to do is you need to take these actions back and then execute it. So you really execute it in the real world, and then it hits. Okay? And of course, the whole pipeline, so this is just a pipeline. It's very simple. Images in, you sample actions, you do physical reasoning in the simulator, and then you get the results, and then you do semantic reasonings with VLM. And you just do this in a cycle. And this thing can be plugged into like model predictive control and do all sorts of things. And I'm going to just show you some results. Okay, I have a few minutes. let me just show you maybe something on the right or on the left. So these things, we just give them a task. We never see anything before. There's no training. Once you have digital twin, the rest of the things are just zero shot. Okay? And then, trust me, I think it will press. I think so. Okay, press, and I can move on. Okay, cool. Yes. Okay, great. So I have like maybe I'll just spend 5 more minutes. I want to make sure it's only 45 minutes. Is we see a lot of things about using digital twins to do a lot of robotic things. But one thing I mentioned is I think it's really cool if we can combine them and do some art creation and something like that. And I think that would be really exciting. So this is another work that Rendong did recently that we try to see how we can model the interplay between those physics phenomenon and those like generative models, and how can you use them to do some arts, okay? So here we see lots of sketches. Sketches can be nice, they can draw cartoons, and then you can see a lot of cool things. Like, and people have trained generative models on top of these things, which is great. And also shadow. People have been using shadow to do different arts, right? They can use these to do storytelling, or you can use this to create different kind of contour and all these things. But in the past, it seems like these two things are kind of slightly separated. People didn't really connect these two things together. And what we're doing here today is how can we combine shadows and sketches and do something very creative? So what do you think this is? Okay, when someone say dog, cat, okay, so certain animal, okay. And then what about this? Giraffe, okay, it's slightly clearer. And then this one is woman, right? I guess. And then, but the question is, what is she wearing? A beanie, a hat? I don't know, right? So what we're trying to do here is something like this. We want to combine these shadows with some physical 3D objects with their shadows and create some art like this thing. So now it becomes a bunny. And you can see that the shape in the middle goes to the shadow over here, and the rest forms its ear and something. And the giraffe, of course, you guys already guessed it, but if you're with an L, you can do things like that. And then it suddenly becomes a head and things like that. So what we're really trying to do over here is that given a single input 3D object, we want a model that can tell us where you should place, which pose you should place the object and where you should place the light. And also we want the model to kind of predict the partial line drawing. And then when combine these two together, it leads to a certain art. Okay? So then this one will be the only object that's input. We want the system to estimate all these things. And I do want to shout out to give credits to Vincent Bao. He's a like really nice Belgian artist that do a lot of these kind of creative things. I personally got inspired by watching his Instagram, looking at his Instagram, and he said, oh, he's doing a lot of cool stuff. And you can see he's like combining 3D objects with sketches and doing all these cool arts. And so we are kind of doing this kind of as a tribute to him. I think I just really like his stuff. So here's how we do it. I'll just give a very quick. Okay, so give it an input object. What we'll do is first, we have this thing, of course, we can first build a 3D model of these things, and we are going to use simulator to simulate all sorts of possible ways about, okay, different lighting, different poses, and all these things. And this will give us these kind of, first, a set of scene parameter proposals, each of them with different shadows and different patterns, okay? And then once you have these things, the next step we'll do is first we'll feed off these things into VLM and ask them to say, okay, if you look at these things, what kind of art or what kind of drawing can you generate beyond these with these kind of patterns? And at the same time, we'll kind of get the boundary of these shadows and then use these contours to input these things into a generative model. And condition on these two things, we'll start to draw tons of different things. And of course, some of them make sense, some of them don't. And then we'll have another kind of evaluator to evaluate based on their semantics, based on their geometry and all these things. I'm going to go quick, but I can talk about this in more detail later. But overall, basically, we try to have VLMs to imagine these things, and then we train the generative model to generate based on this potential imagination. And then we have a critic to evaluate whether these things really looks like a cat, really look like a dog, or does this shadow actually makes sense in all these things. Because ideally what we want is we want to make sure that the cat doesn't look like a cat without shadow. But after adding the shadow, it looks like a cat. That's what we want, okay? So with that, then we can just get a really nice thing over here. So just to show you a few more results, I think I really like is you can see that with these kind of age, you can have this like, woman doing this like, genetics thing, and then dragon pillar, and then penguin. And the nice thing about these things is we can do this for multi-object. You can place them into, you can put them into, drop them into random places with different poses, and you can just be very creative in different parts of the art. And yeah, and that's, I really like this video, so I would just let you see how it looks like how Random really did this thing. And I guess at the end, if you want, you can just go on the QR code. I think we have a lot of more results on the project webpage. And I think it's really cool and it's really fascinating, especially for people like me who are not good at art. But now with AI, we can kind of do something in this space. Yeah, and I think, yeah, at the end, these are the few works that I talked about today that are already published. The rest should be on archive soon. And then, yeah, at the end, I want to thank my students and collaborators. They're the one that make this happen. Thank you.
Thanks Wei-Chiu for his very impressive talk. And here's the Q&A section. And does anyone has a question? Please raise your hand.
Thank you. Hi, thank you for the great talk. My question was about the sim to real transfer that you had, and you talked about aligning what the visual embeddings might look like. But I believe, correct me if I'm wrong, you mentioned that this might need to be done on the task itself. So you have to get the visual embeddings of the real world robot doing the task and the digital twin doing the same task to align them. I'm curious if you have any idea why you can't have something else just like motor babbling and anything else that's not performing the same task to do that kind of visual aligning.
So I guess the question was, if we do those alignment, do we need to do for exact same task, or can we align with other tasks and then do these things? So I think my students, they tried, but I guess it's just like if you align based on the exact same task, of course it performs better. And I would say it's kind of, because the way it really happens is, okay, when the robots are moving and the robot kind of move very slow. So when you start moving, you can just directly simulate the exact same thing in a simulation. So that's very fast. So I think the overhead slightly is not that hard, not that bad, I guess. But yeah, I think the answer will be we tried, and then seems like doing on the same task aligns the better. And because also different tasks, the shadow, all these things are slightly different. And when you move stuff, all the things changed. So that wouldn't align that well. Yep.
Hi there. Thanks for the talk. I like the art piece at the end. So maybe this is a question on like two different ways you could think of robotics and the way you use synthetic data or learning mechanisms. I mean, the way you're proposing is you're going to have very accurate digital twins. You can simulate things. A different way might be, what if these foundation models just get very good at understanding video and the world, and inside them you have knowledge of physics. It's maybe not in the way you want in like the physical properties of the materials, but they do understand a lot of things. So do you imagine these could become ways you could learn directly from video without having to build very accurate digital twins? Or where do you see these two different ways of learning from the real world helping robotics?
Yeah, okay. I personally, if it's me, I think these two things are kind of complementary, right? Because I think, like Sabrina suggested, these models, they have they've seen so many things. They seem to generalize well into different cases, so they can definitely provide a lot. Of course, sometimes the physics might a bit off, just perceptually looks great, but they can serve as a very nice thing to like pre-train all these like the model to give them a really strong prior. And I think the thing that I'm suggesting here is more following the real to sim to real pipeline, where you're just getting in work in the one single place. So maybe the setting is more like, I ordered a robot online, and while the robot is shipping, I scan my kitchen, and then start training the digital twin, and then when the robot arrives, I just download the policy, and it only works in my kitchen because that's the only thing I care. So I think it's kind of in the two, this thing is kind of on one extreme side, but I can definitely foresee at least two things can be like combined together. You can use these video models to potentially build tons of digital twins at a larger scale, but might be slightly off, and you can use tons of domain randomization to solve these things. And maybe these things that we do, plus some interactions, it can provide you maybe very high quality, very fine-grained, like last piece of fine-tuning data. So I think they can be used together. Yep.
Hi, my question is, during the scan, what kind of device you need? Is just a regular camera would be fine, or you have to need like a LiDAR or something?
Oh, so all these things we scan is just an iPhone, just a simple iPhone. I think the most we did is we used Polycam, the app called Polycam, but even for a lot of them, we just use a native video. Yeah. So I think for the objects, for instance, the objects that, wait, let me think. So for the robotics work, I think all of them are just using simple camera app. But for the artwork, I think random use Polycam. Yeah, we don't use any LiDAR or these things. But of course, with LiDAR, or if you use ARKit on phone, it will just make it better because you have IMU, you have LiDAR, it will just make the 3D better.
Okay,
yeah.
Thank you.
I just recently had to move into a new apartment, so I'm dealing with the new kitchen thing, and you'll have drawers that kind of you have to jiggle to open, and cabinets that don't have a handle. So how are you going to kind of deal with those types of real world situations where, the doors aren't going to all open the same, or the cabinets are going to be a little bit funky?
Yeah, so actually, okay. So I went very fast, but once we have these templates, right, we actually, like I mentioned, we have a differential rendering step where we try to fit these templates such that they render nicely into 2D, and also they also fit the original 3D geometry. So in our case, if you just have a normal template, if you just have a weird handle, it will actually deform the mesh a bit to fit those things. But of course, there's limitation in the sense that if the mesh topology is completely different, it cannot do that. So I think, but in that case, I think nowadays, I think when we started this project like roughly 2 years ago, I think 3D generation things are still not as good. I think now there's a huge leap. So I definitely think you can just combine, for instance, take a few images and try to directly generate a 3D shape directly for this particular thing. I think that can definitely help. And regarding whether you say inside is different shape or those things, because in our setting, we assume we didn't see anything. So we just kind of assume, for instance, it's kind of like canonical or standard thing. But one thing that we're looking into now is, can we build up this work to first form a prior about the kitchen, and then once you have interaction, once you observe more, and you update these things correspondingly. So in that case, you'll see, you can imagine what we're trying to do is, we have a kitchen, we have a drawer that's like rectangle, but when you open, if things start looking different, how can you update the geometry and things to reflect that? Yep.
Sorry, just a follow-up question. How many coffee cups did you break?
Yeah.
Do I really need to answer that? That's a joke. Yeah, I thought that's a joke.
Thanks for the talk. And I've seen that you mentioned in Xsim that you only care about the trajectory of the object and you do not care about like the actions of the gripper. So you try to train the policy of the object in a try to train the policy, but you don't have a gripper or something, a humanoid hands. How do you, it's not physically plausible. How do you train the policy? Because it's floating in the air.
Oh, okay. Maybe I was, it's not clear enough. So from human video, you see how objects move. So that's the target trajectory you want, right? But
Yes.
in a simulation, if you didn't pick up the object, then the object will not move. So you still, our agent needs to still pick up the cup. If it didn't pick up, it cannot move the cup, right?
Yes, but you mean that you still have a gripper in your simulations, or?
Yeah.
Oh, okay. So what do you mean you only care about the trajectory of the object?
What I mean is I don't care about whether human grasp it this way. I don't care about where human grasp the object.
Okay, I see.
I only care about how the object moves. So then in the reinforcement learning agent, they will try to use their gripper, grasp whatever place they see fit that can lead to the exact same trajectory.
But what about the videos that you lift with your hands? You have, do you have some demos that you lift the object with your hand? Do you max the hands out, or you only use the gripper in simulation?
Yeah, so I think it's just that, let me just maybe show the video if that's easier. Maybe, yeah, this video. So you can imagine if you have top left, it's your observation, and then you can just track the object's pose. So you can just replay the same thing in simulator. And that's the target. You want the object to follow this object pose trajectory. And then you start using your robot arm to grasp whatever things.
Okay, thank
so
you.
we do track the pose, yeah.
Just one more question. Oh, Sorry.
So in the beginning, we discussed how simulations can be expensive. For example, the gaming scenario.
Mhm.
So how does the cost for a digital twin compare to a simulation? What is the proportion?
Okay. If you are talking about the actual cost, I don't think I have an estimate, but let me just give you an idea. So usually when I'm saying the cost is like the money you spend to build assets, right? And if you have artists to look at this room and start building assets, it's just taking a lot of time. So what we're saying is instead of having artists to do these things, we can use this with scanning, with different generative AI models to automate this pipeline in order to make sure that you have a lot of kind of these one-to-one digital assets without human in the loop. So ideally, the cost will be just like, I don't know, if you can think about there's graduate students cost on developing the pipeline, you amortize it, and then GPU costs on running inference on these things. But instead of but you don't need artists to really look at this thing and then do it. Yeah, if that answers your question.
Yeah, thank you.
Thank you. Let's thank Wei-Chiu again for his inspiring talk. Yeah, and there will be a lunch break and then individual meetings.